My dear students, I'm going to discuss with you some problems of electric potential. You know very well if there is a charge Q and at this point, which is at a distance R, what is the numeric value of potential at here? That is a constant. If I suppose that the medium is free space, then its value is 9 into 10 to the power 9. Then this charge, which is a source charge Q, and the distance R. If the charge is positive, potential will be positive, and if the given source charge is negative, then the potential will be negative. And potential is a scalar quantity, not having any direction, only the numeric value. Now the problem is like if I'm having a dipole minus Q and plus Q, okay, and the total distance, the length of the dipole is 2e. You know very well what is the dipole moment. It is minus to plus. Dipole moment is a vector quantity, okay, and it is charged into the 2e. So dipole moment is charged into the distance, length of the dipole. Now my problem is, what is the potential, what will be potential at this point P due to this dipole? Let I call this point as E, this point as B, this is the center, okay, and center to point P, the distance is R, or you say R vector, the position vector, and let this angle is theta. Now this is a line BP and this is a line AP. Now before going to expression, what is this length BP? Very simple. You apply the cosine formula. From here to here the length is E. Cosine formula is this length BP will be the square root of this R square plus A square minus 2 this into this R into A, then cosine of angle between the two. The angle between the two is theta, cosine of theta. And from here BP, R square is taken as common. R square is taken as common, 1 plus, because there is no R square, it comes in the denominator. There is single R, so it becomes R in denominator, cos of theta, right? And BP becomes, this becomes R only, 1 plus A square upon R square minus 2A upon R cos theta and power 1 by 2, because the square root. Okay, now because our dipole length is very, very small, this A is very, very small as compared to this R. Mean A upon R is less than 1. Then the value A square upon R square will be negligible. Negligible. Okay, so it is neglected from here. And we are having the BP now value, which is R. And now I am applying the, okay, no, sorry. So this is neglected, it is 1 minus 2a upon r cos of theta and power 1 by 2. Now similarly, you can find the value of AP. Now here angle is 180 minus theta, because this is theta, total angle is 180. Now what is AP length? Okay, AP length like BP. AP is under root of, like this line square plus this line square minus twice this into this r into a cos of the angle between the two, 180 minus theta. So cos 180 minus theta is minus cos theta. So it becomes, AP becomes root of r square plus a square plus 2re cos theta. Now here it was minus sign, here it is a plus sign. So it implies the value of AP becomes r 1 plus 2a upon r cos theta and half. Now I am going to write the potential at here because of the dipole. So potential at here is potential due to this charge and potential due to this charge. So potential at point P is equals to potential because of charge at B plus potential because of charge at A, at here. So VB plus VA. Now what is VB? VB is constant. Then this plus Q, this plus Q upon the distance, which is BP. Right? Now similarly you write the potential because of the charge at E, VA. It is constant. Now the charge is minus Q. So minus Q upon the length AB. Now just take the sum of two. So the potential becomes, total potential becomes constant Q upon BP plus and minus because of the negative charge, constant Q upon AP. Plus into minus, this is minus. Now here, substituting the value of PP here and AP here. So potential becomes constant Q, and it becomes BP, 1 upon R, 1 minus 2A upon R cos theta raised to power minus 1 by 2. Minus because the whole term was in the denominator. So I place it in the numerator, so that's why power minus half. Don't forget it. Now then minus constant q, then 1 upon AP, 1 over AP mean this upon R, then 1 plus 2a upon R cos theta, and raised to power again, it was in the denominator, now I place in the numerator, so power minus 1 by 2. Now this becomes constant q by R, applying the binomial expansion. And what is binomial expansion? Very simple. I am going to write only two terms. So minus 1 by 2 is taken here. So 1 minus 1 by 2 becomes plus. And 1 by 2 and 2 cancels. A upon R cos theta. And this constant q upon R 1 plus, and this minus 1 by 2, it comes here. So it becomes a negative sign. And 2 cancels. A upon R cos theta. Now total potential becomes constant q by R common 1 plus A upon R cos theta minus 1 and minus plus A upon R cos theta. Okay, this minus 1 and plus 1 cancels. So what about the result? So the result is V is equals to constant q by R, A over R cos theta, A over R cos theta, 2A over R cos theta. Now you know very well what is q minus q plus q, the length 2a. Q into 2a, charge into the length of the dipole, is the dipole moment P in magnitude. Okay, so replacing Q into 2a with P, the dipole moment, and R becomes R square. So potential is constant P upon R square cos theta. So this is our Z. Now, one thing is very important. If there was a single charge and potential at here at a distance R, that potential was constant Q by R. So that potential varies inversely with single R. But in case of the dipole, potential varies not with single R, but with R square. So that is the rapid decrease or increase of potential with R. There is more effect of R in dipole as compared to monopole. Monopole, the variation is with single R. In dipole, the variation is with R square. So this is very important. Now next, because in our case minus q plus q, the observation point was here at an angle theta. If you take observation point here, then theta decreases. If take here, theta still decreases. If take here, theta becomes 0. So if observation point comes here, theta becomes 0. And if your observation point is on the other side, theta turns to pi. So what happened here? So if theta is equals to 0, mean observation point at here, on the axial line, if the observation point is on the axial line, theta equals to 0. Cos 0 is 1 and potential is simply constant P upon R square. And if your observation point is on this side, then theta equals to pi. And theta pi means cos pi is minus 1. So potential becomes minus constant and P upon R square. Now next, this is a dipole. Observation point was here at an angle theta. Now if your observation point is at here mean perpendicular to the dipole axis, it is called equatorial line. This line is called equatorial, and here angle theta equals to 90 degree. So if the observation point is on the equatorial line, what is cos 90? Cos 90 is 0. So potential here turns to 0 value. So no potential on the equatorial line because theta is 90. Cos 90 is 0. So potential becomes 0 at here. It is 0 at here, 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 0 at here. So the whole line potential is 0. So for potential, this line is called neutral axis. For the potential, this line is neutral line because potential is 0. We may think otherwise also. If minus q and plus q, this is a equatorial line and your point is here. And what do you think about potential otherwise without expression? You will say potential at here constant minus q upon this distance, this is AB, plus potential at here because of this constant plus q upon BP. AP equals to BP. This length and this length, they are equal. Length are equals, plus minus, so potential becomes 0. That's there. Okay. Now next I am coming. What we mean by equipotential surface. Very simple. Like this is a charge, okay? And around the charge, you draw a sphere. Sphere means like a ball. A surface like a spherical ball. So this is a surface, okay? I draw a spherical surface like a ball. What is potential at here? constant q by the radius. And potential is a scalar quantity, no direction. What is potential at here? The same. Constant q by r. What is potential at here? The same. Constant q by r. So at every point on the spherical surface, the potential, the value of the potential is the same. So this surface is called equipotential surface. Means potential is equal at every point on this surface. Okay. Now one thing is very important again. If like I'm having a charge Q, this is a point B, this point E. This distance is RB, this distance is RE. You know the value of the formula of potential? Constant q by r. If charge is positive and distance is less, then here potential will be greater. And because the distance of A is greater than the distance of B, so if distance is greater, potential will be less. So at here the potential is less and here the potential is more. Then what is VB minus VA? VB minus VA means potential difference between B and E. What is the definition? Work done in bringing unit positive charge from A to B. Because you are bringing this charge, source charge is positive, you to do the work against the repulsive electrostatic force. You to do the work from A to B. And whatever the work done from A to B, that work done from A to B per unit test charge becomes the potential difference. Now if I say this is point A, this is B, here the potential difference is 0 because VA equals to VB. If potential difference is 0, work done will be 0. So if I am carrying a unit positive charge from here to here, then no work will be done. For unit positive charge, or you can say for any other charge, no work is done from one point to another on the equipotential surface. This is very, very important. No work is done. And one thing more, you know very well the definition of electric field with potential difference. The work is E vector dot dl vector. This is from that expression. Electric field is equals to the negative of the potential gradient. So basically for unit charge, the work done is the potential difference. Okay. Or remember dw is E vector dot dl vector. If the work done is 0, you know E dot dl means E dl cos theta. What is theta? Theta is angle between E and dl. If the work done is 0 and if there is E, there is dl, but work is 0, implies what? Cos theta equals to 0 implies theta equals to 90. Mean the angle between E and dl will be 90 degree on the equipotential surface. Like this is equipotential surface and dl will be over the surface and E will be perpendicular to the surface always. Like this will be the direction of E, perpendicular to the equipotential surface. So this is equipotential surface, E will be normal, perpendicular. So this is very, very important. And remember, okay, I'm not going in detail. If you want to ask any question about equipotential surface, you please write me in my description box. No problem to me. Okay.